So far, you've learned 5 different tests to determine convergence and divergence for series. We learned geometric, nth term, telescoping, integral test, and then p-series was our last one. Geometric series was very specific. It had to do with the ratio. We always multiplied by a common ratio. We were looking at whether or not that ratio was greater than or equal to 1 or less than 1. When we went to nth term test for divergence, this is the only one that only tests for divergence. But if the limit, as n approaches infinity, of that sequence of numbers, if the sequence is not approaching 0, then I know that my series is going to diverge because I'm not going to be able to add smaller and smaller values. So that is one of the really easy tests, but it only does divergence. Then we talked briefly about telescoping. Telescoping is not AP tested, but it's this idea of these terms kind of collapsing on one another. And when those terms collapse, we're able to take this limit and determine that it is approaching a very specific number. So that's kind of this sum, right, approaching a specific value. So telescoping is pretty unique, and again, it's not AP tested. Then we went on to integral test. Integral test is a application of improper integrals. It does have conditions. If the function is not positive, continuous, and decreasing, then we cannot apply the integral test. So you always have to double check those conditions when you are evaluating this piece. So then we set up the improper, we determine if the limit is approaching a value or if it's infinite. And obviously if it's infinite, that means that no limit exists, so the series diverges. This was an example of the series converging, positive, continuous, decreasing. We used arctan for this. And then we ended up with a value because our arctan limits do approach a specific number. So that means that the series converges. Also with the integral test, we talked briefly about this idea of remainder. So with remainder, we do have to pay attention to basically we're finding the error. So if I find an approximation, a partial sum up to, in this particular case, it was the 6th term. This is my partial sum using 6 terms. If I integrate this function from 6 to infinity, I'm going to find the max error. So that's the idea of the remainder with integration. Then we talked about p-series. So p-series is very straightforward. You're going to have a term in the bottom raised to a specific power. We looked at something called a harmonic series. And then we looked at the values. If p is greater than 1, we're going to converge. If p is less than 1 or between 0 and 1, we're going to diverge. And then if p is actually equal to 1, that's called a harmonic series, and that also diverges. We double-checked these using the integral test. So all of these were basically an application of the integral test. So today we're going to do comparison tests. And the first one that we're going to talk about is direct comparison. And what we're going to do is we're going to take our knowledge mainly of geometric and p-series test, but we could use other tests, and we're going to compare our series to another series. So if we're going to talk about a sub n and b sub n on these, so if n is equal to 1, the a sub n is going to be whatever the smaller series is whenever I start talking about this. Okay, so the smaller values, and then the b sub n is going to be a reference to the bigger series. Now, I really like direct comparison test, but there's also a thing called the limit comparison test, and we'll talk about that as well. And usually we can use either or, but sometimes direct comparison is a little bit easier. The idea is if I am going to take a series that is bigger, and I do analysis on it, and I find out that this bigger series converges. Maybe it's geometric, maybe it's a p-series, whatever it is. But then I compare it to a series that is smaller. We do have to deal with positive series here. If I know that this piece converges, and this piece is going to be smaller, then the series the A sub n series also converges. So another way to think about that is smaller than finite is also finite. Remember, converging means I'm going to a specific number. So if this is smaller, I'm also going to be going to a specific number. We can flip that a little bit, and we can say that if the smaller series diverges, and A sub n is still less than or equal to B sub n, then that means the bigger series also diverges. And another way to think about that is bigger than infinite. If this is bigger than that, and that already diverges, bigger than infinite is also infinite. So let's do an example of that. The hardest part about this is determining what to compare to. This is the series that I'm analyzing. You have to figure out what you want to compare to. But usually we want to work really basic. We're not trying to go fancy. We're not trying to come up with anything crazy. I want to compare this to something like a geometric series or a p-series if at all possible. And this is going to behave very similarly to the 1 over n cubed. The plus 1 is the only difference. So we're going to compare to 1 over n cubed. So if I'm looking at just this is the analysis that I'm going to do for right now. I know that this is a p-series. So I'm going to say p is equal to 3, which is greater than 1. And therefore, this specific series, now I don't want to just say the series for this one because now I'm talking about two different series. So I want to say this series, I want to go ahead and write it out again. That one is going to converge. And it converges by the p-series test. So here's the rest of the analysis. If this series right here converges, the question is this series always going to be less than this one? Because if so, then I'm going to be able to say that this one also converges. So we are doing a comparison between this series and this series. So because this is a denominator, if this is a 2, I would do 2 cubed plus 1 and 2 cubed. This would be 1/8, and this would be 1/9. Well, that's going to be less than. I could keep going, but because this is in the denominator, this series is always going to be less than for all n values. And since that converges, sorry, I should have put values there, but since this converges already for all n, that means that this is also going to converge because of the comparison piece. So now we can say that this specific series that we were asked to analyze to begin with converges by direct comparison. By direct comparison test. You do need to put test there. I should put by p-series test right there as well, just to clarify. The hardest part is determining what do you want to compare to.